So, so we're going to stick with sound waves today. Although what we're going to talk about, this is true of all waves, once again, all right? But we're going to really demonstrate it with sound waves. So the very first thing that we need to do is I need to give you some vocabulary, all right? The very first vocab is natural frequency. And I just realized nobody's showing me their faces. Not even my regulars. Oh, all right. I got some regulars. At least one. You guys can't leave her hanging. She can't be the only one. So anyway, natural frequency. It's the frequency that an object vibrates at when it's struck or when it's plucked. Okay? Basically, when there's some sort of force that's acting on that object. So I'll give you an example of that. If I have a tuning fork, okay, I pick out a random tuning fork. This tuning fork has stamped right on it the frequency. It says 426.6 hertz. All right? So anytime that I hit it, it's always going to vibrate 426.6 times per second. And it doesn't matter if I hit it soft, or if I hit it hard, or if I hit it with a different kind of mallet. Like, it always makes the same sound, right? It always makes the same sound because its natural frequency is 426.6, so it's always shaking the same number of times per second. Wait, say that again? Oh, thanks. Thanks. All right. So it's always going to shake the same number of times per second. Now, every object has a different natural frequency. So if I look at this tuning fork, this tiny one, it's got stamped on there 2,000 hertz. So because it's smaller, when I hit it, it has a much higher pitch sound. You guys hear that? And it doesn't matter how hard or soft, once again, or how many times I hit it, always has the same sound. Now, if I have a bigger object, like let's say I have this tuning fork. Now, this tuning fork it's not stamped on here, but it's 200 hertz. So when I hit this one, the tone is much lower, right? And no matter how many times I hit it, it's always going to shake at 200 times per second. Does that make sense? So think about, does anybody in here know what a carillon is? What? Carillon? No. Okay. So a carillon, it's a collection of bells. And they're usually like, in a church tower or like up in some sort of steeple. So have you guys ever been to the Botanic Garden? Okay. In the Botanic Garden, they have a carillon. So if you walk out like on the, I'm trying to think, south side of the property, there's like little islands that you walk, and there's this big tall tower, and in the top of that, there's a whole bunch of bells. Now they play music on those bells. And if you look in the bottom of it, it kind of looks like a piano where they play the music, except they're like, big levers, okay? And there's one lever for every single bell, because every bell can play how many different musical notes? One, right? Every time you hit that bell, it always plays the same sound, right? And so they have those bells, they made them so that one would play, a middle C, one would play an A, one would play a D, right? And the person who plays the music, they're basically pushing and ringing those bells. If you ever go to U of I, well, like for college or something, there is a carillon there as well. So there's a big statue when you walk onto campus. It's called the Alma Mater. It's got 3 people. And right behind it, that's the math building. It looks like a castle. It's called Altgeld. And in the top of Altgeld, there's a carillon. And they play music. It's pretty much like the same 4 songs. They play the Flintstone song a lot, right? Like, I don't know why, but once again, I mean, but they play it. Each bell has one note, and that one note comes about because of the natural frequency. Another good example of that, you guys too, is if you've ever seen people with like a collection of people doing music with bells. Like sometimes you'll see this around the holidays, like around the Christmas holidays or whatever. if you make music with actual handbells, you need like 10 to 20 people because everybody's responsible for like one or two bells, right? And it requires a lot of coordination actually to do it. It's pretty cool, and there's a song called "Carol of the Bells." If you YouTube it and look at an actual performance of it, you'll see like how many people are required to actually do that, because each bell is just one musical note. All right. Okay, now the reason that we're talking about natural frequency is because of this other thing called resonance. And this word I know you guys have heard before. Maybe not in a science aspect, but haven't you heard people say like, "Oh, that really resonated with me," right? So that use of the term actually does come about because of physics. It is actually originally a physics term. And this is what resonance is. It's when one object vibrating at the same natural frequency of a second object makes that object start vibrating. So when you say something resonates with you, you're basically saying like it moved you, right? That's what's happening in resonance. So I'll give you an example of that. I have two tuning forks. These aren't exactly the same. Hold on. Okay. So I have these two that are both 426.7. So I have two tuning forks that are both 426.7 hertz. All right. Now, if I strike this tuning fork, and then I put it next to this tuning fork but don't touch it, this second tuning fork will start vibrating. All right? Because this one is sending out waves at the same natural frequency of this one. So this one already wants to shake at 426.7. This one's sending out waves at 426.7. So when those waves hit this tuning fork, it'll start making it shake. And usually I would pass these around. I have extras so you guys can test this out. So when I hit this one, I'm going to put it next to this one. And I put it to my ear, I can hear it. Like you guys might not be able to, but I'll bet you they can hear it at home if I put it on the mic. So I'm going to test that. Could you guys hear it or no? Was my mic not good enough? Oh, you couldn't hear it? So I can hear it. I guess at home you're just going to have to trust me. You guys, I have other sets of these, so I'll just put them on your desk and you can test it out. But it works, okay? So anytime that I have a set of waves that are coming in at something that match the natural frequency of the object, that it'll start to shake. So let me ask you guys this. Do human beings have a natural frequency? Like if you strike them, hopefully not violently, right? Like let's say you're just goofing around with your friend, you give them a gentle shove, right? Like a push, like get out of here. Will their body start shaking at a certain number of times per second? Like, yeah, most people would say no, right? But I want to ask you this question. Are there any waves that when they're coming at your body that you can feel?
Yeah.
And that would make you start shaking? What would they be?
Like really loud bands.
Well,
Loud,
yeah, but
just noises, I guess.
yeah, but there's a very specific noise. Oh, the bass. Can't you feel the bass?
Oh yeah.
Right? So if I'm at like some 80s revival of Van Halen or something, and he's out there like with the guitar doing those super high notes, you can't feel them. Doesn't matter how loud they are, you don't feel them. But as soon as they start plucking the bass, so that would have been like Primus back in my day, if you guys know. No, all right. It's a good band. I think it's high school appropriate. So anyway, we listened to them in high school. They're very famous for their bass player. He was like the feature. So as soon as the bass player would start playing, you can feel the bass. There might even be songs about that, right? Like feel the bass and all that. So anyway, that's very close to your natural frequency. The natural frequency for human beings is actually subsonic, meaning we can't hear that sound. but it's around 15 hertz. Okay, so if I play a sound at 15 hertz or even close to 15 hertz, which the bass is close to it, then your body will start shaking. Okay, now here's the crazy thing about resonance is that it creates a feedback loop. All right, so we learned. Let's see if I put it. Actually, here, hold on. Before we talk about that, so we learned yesterday about interference. So if I have a wave that's like coming in and hitting my body, right? And then my body is shaking. Well, doesn't it actually reproduce that wave? Right? And so my body will send that same wave back out. So this one's coming into my body, this one's going out of my body. Well, won't those two waves intersect? Won't they occupy the same space? So then they'll start interfering, right? And the waves will get bigger, actually. So when the bass is coming in and your body's shaking, you're actually adding to the bass and you're making the bass louder. If that makes sense. All right? So this is how, have you ever seen someone like breaking a wine glass with their voice?
Yeah.
Okay? That's how this works. It's because of resonance. So if you ping a glass, it'll shake a certain number of times per second. It'll make a certain sound. Now, if I'm able to reproduce that sound with my voice, all I have to do is send that sound with my voice at the glass. The glass will start shaking. It'll add to the waves, which make them bigger. And if I do that long enough, the waves get bigger, 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 until the glass shakes so much that it breaks. Right? That's resonance. In fact, I show in a normal year of physics, you guys, I show exactly one movie, like in its entirety. It is a whole 20 minutes long. I actually made a digital copy of it and put it in Drive. So that's like your quote unquote homework if you want. Watch the movie. It's actually very good. It's old. Like people have maybe mullets in there and stuff, right? But I don't know who would ever have a mullet. I don't know. It's some weirdo, I think. But anyway, if you watch it, it explains this whole thing. And there's some very, very cool footage of like Ella Fitzgerald. She's a famous jazz singer breaking a glass. Or the Tacoma Narrows Bridge, if you guys have ever heard of that. It's a bridge in Seattle that fell because of resonance, broke apart. And when you watch it, by the way, if you watch a video, even if you just watch the first few minutes and see that bridge, that's concrete. That's flexing and going crazy.
What sound made it collapse?
So this is what happened, and I'll talk more about this in a second. If I have a string, and I pull it tight and I pluck that string, the string will shake a certain number of times per second. It arrived, Mr. Komet. It's pretty awesome. It is. We're going to start setting it up today. I got the labeler out and everything.
What's the plug for?
So you can put that into the wall outlet, and then you can plug in all your power tools there.
Nice.
I think it even has a USB cable.
Oh.
So I super appreciate it. Thank you.
You're one of those people I favor and I do lots of things for.
Yeah, whatever. As I tell everyone else, you just have to ask. If you ask for things,
got your
sometimes you get them.
haircut, Finally.
I didn't just get a haircut. I got them all cut.
Oh God.
Kayleen does not like that joke. You know what else she doesn't like? She really hates it when I call when I say roomies and zoomies. See?
Very nice. Very nice.
It's a running joke in our next class how much she hates it. I can't say it because she hates it.
That's good.
Yeah.
Good. All right, sir. Have a good day.
All right, thanks, you too. So anyway, guys, so if I take a string and I pluck the string, like on a guitar, right? The string's going to shake a certain number of times per second. Well, isn't a long suspension bridge basically a string?
Yeah.
So if I take that suspension bridge and push wind on it at a certain, so that the wind is basically plucking it at a certain frequency, what'll happen is those waves start to amplify, and the bridge will start to shake more and more and more and more and more and more till it breaks. So the same thing happens actually this is kind of getting a little bit off topic, but not really. If you look at the Sears Tower, have you guys ever been like at the Sears Tower? So now I don't, now they have more security measures and stuff. So I don't know if it's still possible, but I think it is. If you walk right up to the Sears Tower, all right, and look straight up, it's very disorienting. And the reason it's just like you'll feel like you're swaying, like you'll start doing like one of these things, right? And the reason that happens is because the top of the Sears Tower, we're used to buildings not moving, right? But the top of the Sears Tower moves 6 feet in each direction. And it's because of the wind. Actually, if it didn't move at all and there was any earthquake or whatever, it would just break. And you guys know that we do have minor earthquakes here, because the major fault line runs through Missouri and down into Mexico City, actually. So if you look up there, you think you're moving when actually it's the building that's moving. The building is moving over the top of you and then away from you. So all buildings and stuff are like this. And basically what you have to do, and this actually is in the video as well, you have to build the building so that the height of the building won't match the resonant frequency of the wind or the earthquake waves. So the last major earthquake, major earthquake in Mexico City actually happened when I was your age. I want to say that was 85, and I was in high school. And it just devastated huge parts of Mexico City, because what happens is, and I'll explain more of this when we do open and close pipes, is that if I have a building and it starts shaking back and forth, right? So I have an earthquake wave and the wave is approaching the building. The earthquake wave will go up the building, so it'll make it shake this way. And then what happens when the wave hits a boundary? It does what? It flips sides. So it'll flip over to here and come back down. And so that would cause maximum shaking at the top, and it'll most likely break the building apart, right? And so in Mexico City, most of the buildings at the time were 10 stories, and all of those buildings got wiped out because of resonance, right? So now, they do things different, hopefully, right? Supposedly. But San Francisco is another place that's on these fault lines, right? So the buildings have to be very specific heights, and then actually underneath these buildings, they're kind of like on springs, so that the building can jostle on these ginormous springs and not start shaking side to side as much. Like, it's all, like, once again, physics is awesome, you guys, right? Once you get into it. So, in order to understand like more of how these things work about musical instruments, tuning forks, we need to define what a standing wave is. So we made a standing wave with the Slinky for everybody who was here. Do you remember when we were moving our hands side to side and it didn't look like the wave was moving forward and back, it just moved like the Slinky was moving up and down? You guys remember that? So a standing wave is a wave that matches the exact wave that's being reflected. So if I send a wave in with the Slinky, I move my hand, I send this wave in towards, say Kayleen, you're holding one side, I'm holding the other. Then when it reflects, that wave will reflect back so that it exactly matches the wave that was sent in, right? This is what we call a standing wave. So on the Slinky, it looked like the Slinky was just moving up and down. It didn't look like the pulses were moving back and forth between us, okay? So a standing wave has what we call nodes and antinodes. So the antinodes are where the Slinky isn't moving, or where the wave looks like it's at the rest line. So that's the antinodes. And then the nodes are where we have maximum disturbance, like up and down, up and down. And so what happens in a lot of musical instruments is that we create standing waves. And then once again, those standing waves, they interfere with each other because they're in phase, they make the wave get bigger, 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 bigger. All right, good so far? All right. This is kind of a hard thing to do without actually experiencing it. So I don't envy you guys. for trying to learn this. It's just something that if you take another physics class, it's going to come up, right? So I felt like it was a good thing for you to know. So we have two different types of pipes that we can make resonate. Now, most of the instruments in orchestra, you guys, work because they're pipes. So think about clarinets, flutes, tubas, trumpets, trombones. All of those are pipes, right? Sometimes they take the pipe and they wrap it around, but they're just pipes. Now, there are two types of these pipes, open pipes and closed pipes. All right? Now, an open pipe will resonate at its fundamental frequency when the length of the pipe is 1/2 the length of the wave. All right? So I'm going to draw out a wave. If I have a wave, like the entire wave, it would start at the top. Here, I'm going to draw the rest line. So it would start out at one end, at the top. It would go down. It would hit the other end. It would go back up, and then it would hit the top again, right? So from the crest to the trough, that would be 1/2 of a wave, right? So if I can set up a wave inside this pipe, what'll happen is it'll resonate when the peak of the wave is at one end, and then the trough is at the other end, because that's the maximum displacement. It'll cause maximum shaking. And then what'll happen is when it hits that boundary, the wave flips, it comes back up here, and it does the opposite thing, right? So on the ends, you'll have maximum shaking of the pipe. So if I take a pipe, and this isn't a good example because it's plastic, but if I take this pipe and I hit it, it'll make a certain sound. You guys have seen these in wind chimes before, right? And in wind chimes, don't they have all kinds of different lengths of pipe? And each one of those different lengths makes a different sound depending on how long it is, all right? So if the pipe is longer, the waves are going to be longer. And if the wave is longer, that means the frequency is lower, right? Because we have this equation that says V equals F lambda. So if the wavelength goes up, the frequency goes down. So the longer pipes always have the lower sounds, and the shorter pipes always have the higher sounds, okay? Think about musical instruments. Like the tuba, doesn't it have the lowest sound? And if you took the tuba and you undid the circles and you pulled it out straight, wouldn't that be like a super long, huge pipe, right? So that's why the tuba makes a bass sound. That's why it makes such a low sound. Whereas if you take like the piccolo, which is like this big, it makes a really high frequency sound because the pipe is so much smaller. So if the wavelength goes down, then the frequency goes up. Does that kind of make sense? Now, for closed pipes are closed on one end, so they'll resonate at 1/4 of the wavelength. So what that would look like is I would have my rest line going through, and I would have a wave where it goes from the rest line to the peak, and then to get a whole wave, I got to go all the way off of here, right? So this, from the rest line to the peak, is only 1/4 of the wave, right? Because then it has to go back down to the rest line, down to the trough, and back up to the rest line. So if the crest is at the end, once again, that'll cause maximum shaking, and then the wave will flip, and it'll go down here, it'll hit there, it'll flip again, and on that open end of the pipe, because a closed pipe only has one open end and it has one closed end. So on the open end of that pipe, it causes maximum shaking. So I could show that right here. I have all these tuning forks, right? They're all different frequencies. So I'm going to hit the tuning fork. And for everybody at home, I have a big graduated cylinder and it's got water inside of it. Okay? And then I have this pipe that I'm putting in there. And because it's got water, that closes one of the ends. Okay? So what I'm going to do is I'm going to strike this tuning fork. I'm going to put it over the pipe, and I'm going to move the pipe up and down until I get a loud sound. That would that would mean that this frequency of sound matches the resonant frequency of this pipe. So let's see if we can get it to work. You guys hear that? And if I go up, get soft. So it works, right? Physics does work. Could you hear that at home, Chantel? You could not. Let me see. I don't know. Let me see if I can get it closer to the mic. Then you won't be able to see this. So I'm going to try it one more time. So that's loud. Not loud. Could you hear that? No. I'm so sorry. Yeah, I don't know how to fix that problem for you guys. But so if I do a lower frequency, it'll resonate at a longer wavelength. So let's try to do it with one of these big ones. Maybe this will help. So I'm going to do it with the big one. Oh, I can't get it long enough. That's too low of a frequency. Let's see. How about 256? Did you guys hear it? It's right there. So lower frequency, longer wavelength. I had to pull it out higher, right? And in fact, with this 2000, so that one, I couldn't pull it out long enough. With the 2000, I can't make it short enough. I can't make it short enough to make it resonate. So, this, just so you guys know, this would be a lab that we would normally do. And I would have you figure out the speed of sound using this, right? Because if you know the frequency and you know the wavelength, then you could figure out the speed, right? So, maybe next year. Maybe you could come and do it as like for funsies after school. We could have physics club. You could keep me company after 2:30 and do fun physics experiments. So how this works out in a problem, like I'll give you an example. This is a sample problem. So I have a sound wave, and that sound wave is traveling at 340 meters per second. What would be the frequency of the wave if it's resonating in an open pipe with a length of 6.75 meters? So that's my problem. So let's figure out how we would solve this. All right? We know the velocity of the sound. We don't know the frequency. And I know the length of my pipe is 0.675 meters. And I know that it's an open pipe. It says right here it's an open pipe. So for an open pipe, the length of the pipe is equal to 1/2 the length of the wave. So if I know the length of the pipe, I could figure out the length of the wave, right? So I would just stick in 0.675 here. And then to find the wavelength, wouldn't you have to divide by 1/2? Or dividing by 1/2 is the same as multiplying by 2, right? You guys know that from math. So these would go away, and the wavelength would end up being 1.35 meters. So then if I know the length of the wave, and I know the velocity, I can figure out the frequency. Because velocity is frequency times wavelength. And the velocity is 340. And the frequency we don't know. And then the wavelength would be 1.35. So if I wanted to solve for frequency, I would divide both sides by 1.35. And I get like 251.9. Thank you. 251.1? 9 hertz. So that would be fairly low frequency. It would be a bass sound. So really, like, no new equations, but what you do need to know is for an open pipe, like, write this down. For a closed pipe, the length is 1/4 of the wavelength, right? Just write it with your equations, so it's all in one spot. So for a closed pipe, the length is 1/4 of the wavelength. Oops. And for an open pipe, the length is 1/2 of the wavelength. Okay, and then, wait, hold on. We did that one. All right, and then actually, you guys, that's where I want to end today. All right, so the reason that we're going to end a little earlier too is that if you have a chance, go and watch that movie at some point. All right, my son's teachers, they actually will show movies during class. My assumption is that you can do that on your own, right? Like, we could use class time to talk and do things, and then you could watch movies on your own. It's not social studies. Just saying. So go do that. Now, there are problems, but just so you know, in order to do most of those problems, we need one more equation. So I would hold off on working on the problems till tomorrow, okay? Because tomorrow we'll get that one last equation, and then we'll wrap up sound waves the next day, and then we'll get into light. Cool? So everybody have a great day. If you need me, I'm here. I just opened the chat window.